Okay, good morning, friends, and welcome back to this to the next lecture on heat transfer. So let me put on my headphones. I believe you will be getting some background noise otherwise. Please give me a minute. Okay. Yeah, I think that should be better now. Good morning, friends, and welcome to heat transfer. Uh, Today, what we will do is we were discussing forced convection, right? And in the last class, we were discussing external flows. So what we will do today is we are going to complete the discussion on external flows. There are very little remain, and then move on to internal flows, right? So at the end of the last class, we were solving a problem. So the problem over a flat plate, flow for off flow over a flat plate, that is. And we at the beginning we said that we figured out that the I think you can see my screen now. We figured out that the flow will be turbulent by the time it reaches the trailing edge, right? So therefore, we discussed that the flow will be laminar followed by turbulent. And going ahead, we solve this. Then what we said was, which is part B, and I asked you to do that in class, at home, is if the leading edge is rough, which means that we are actually inserting or introducing some mechanism by which the boundary layer becomes turbulent, what we call tripping of the boundary layer, right at the leading edge. So therefore, the flow will be turbulent throughout, right from the beginning. Remember, this is artificially done. Okay. If it was a natural course of action, it will start as laminar and then go to turbulent after a certain distance. But here we have initiated the turbulence earlier. Okay. So I asked you to just work out these, to use the appropriate correlations and um, work out the values of the drag force as well as the total heat transfer. So do any of you have the answer?
Sir, I have a doubt.
Yes, go ahead.
Sir, in the first case, for finding the average Nusselt's number, so what should be the value of the coefficient C1? Because in our notes we had written C1 as 14,500 if Reynolds number is 3 into 10 to the power of 5, and 0 if it is if
Turbulent
it is
from the
turbulent from the leading edge. So for the first case in our question, what should the value of C1 be?
that should be 14,500 because this is the transition Reynolds number is 3 into 10 to the power 5. Okay. Did I lose everybody? Can you hear me?
Yes, sir, we can hear you, sir. But the Reynolds number that we had gotten was 4.42 into 10 to the power of 5.
Yeah. So, okay, let me explain this again. The Reynolds number for flow over a flat plate keeps increasing, right? It's a function of the distance x, isn't it? If this is my direction x, Reynolds number is u infinity x by nu. Okay. So what happens is Reynolds number will start from 0 at the leading edge. It will keep increasing as x increases. And then you will reach some value of x, which I have denoted as xc, which is the critical Reynolds number, where, so let me write it again. This is my flat plate, okay? This is x. Yeah, my flow is coming at u infinity, t infinity. Okay. Now the flow will develop like this. Okay. So since Reynolds x is u infinity x over nu, so this keeps increasing with x. Okay. Now, when you reach a certain value where x equal to xc, at x equal to xc, Reynolds number at xc, which is u infinity xc over nu, is 3 into 10 to the power 5. Okay. After this, the flow becomes turbulent. So before this, it was laminar. After this, it's turbulent. So 3 into 10 to the power 5 is the transition Reynolds number. Okay. It is true for any flow. What you did was, what you are saying, that we calculated the Reynolds number to be some 4.2 10 to the power something. I've forgotten how much. Yeah, 4.42 10 to the power 5. That is at x equal to L. Reynolds number will keep increasing with x. At x equal to L, it is 4.42. That's fine. But the transition to turbulence would have happened when it is 3 into 10 to the power 5. Unless you did something else, like, inserting a turbulator or making the edge rough or something. That's different. But in its natural course of action, the flow will develop and transform from laminar to turbulent at a transition Reynolds number of 3 into 10 to the power 5. So in part A, you have to take 14,500 as C1. Is that clear?
Yes, sir. Thank you, sir.
Okay. What about part B? Did any of you do that? Because the C1 problem would not have arrived there. That's not good. Anyway. Like that's what you guys want, but I will write something, we'll just copy. So let it be like that. Okay, that was flow over flat plate. Let's move on to other configurations that we may encounter in external flows. Okay, because the flow can be over a cylinder, can be over a bank of cylinders, etc. So this is, and as I said, that forced convection, most problems, it's correlation based. Okay, so you have to understand which correlation to use under what conditions, and then use that to solve the problem. Okay, so for external flow, we have come up with these flat plate correlations. We have a correlation for average Nusselt number for laminar flow, 0.664 Reynolds to the power half, Prandtl to the power 1/3. Okay, at the local level, its Nusselt number x is 0.332 Reynolds x to the power half, Prandtl to the power 1/3. We have found that. For turbulent flow, the dependence on Reynolds number changes from the index changes from half to 0.8 or 4/5, and you see this correlation. Okay, and for laminar followed by turbulent, this is what we have. This is also a correlation. Okay, now we also came up with flow with unheated length. Okay, which we had discussed last time. So the correlations were all in the form of C Reynolds to the power m Prandtl to the power 1/3, and when you have unheated length, there was 1 minus zeta over x to the power a and the whole to the power b in the denominator. Okay, so you have this correlation. So you have these correlations at your disposal, and you know how to solve them. Okay, how to use them. Only judgment you have is which one to, whether it's isothermal, whether it's isoflux, whether it's laminar flow, whether it's turbulent flow, whether there is an unheated length. So these are the judgments that you have to develop looking at the problem. Okay. So similarly, we have something like flow over a cylinder. Okay. So flow over a cylinder would look something like this. We have seen that before. Let us say this is a solid cylinder. The flow will come like this. And it is going to go past. Similarly, U infinity, T infinity, and so on. Okay. And this cylinder will have a wall temperature TW. So for that, there is a correlation by Churchill and Bernstein, which is given in this form. Nusselt D is H bar P over Kf. Okay. Similarly, Reynolds is also in terms of what is that? Okay. Similarly, Reynolds D is U infinity times the diameter of the cylinder divided by U. Okay. So these are again correlations you don't have to remember. I have repeatedly told you. These correlations will be provided to you. There will be a complete correlation list that will be given. Okay. And you have to pick and choose which correlation to use depending on the problem you have to solve. Okay. So similarly, if you now go to a flow over a sphere, again there you have a correlation 2 plus 0.4 Reynolds to the power half plus 0.06 Reynolds to the power 2/3, blah, blah, blah. One thing that to note here is this term mu over mu s. Okay, what is that? So mu, as we know, is the dynamic viscosity of the fluid. Okay, mu is mu at T average, and mu s is mu at Ts or T wall. Okay. Now, what is T average? T average is often called the mean film temperature. As the name suggests, if you consider the boundary layer to be a film, the mean temperature therefore will be Tw plus T infinity by 2. Okay. Now, this term mu over mu s to the power something becomes important when the temperature difference is very large. So let us say we are talking about combustion, flow in a gas turbine, uh, where the temperatures are very high. The temperature difference between the solid and the fluid is very high. In that case, this becomes important. But otherwise, if we are dealing with not so high temperatures, that is Tw and T infinity are not so large, such that the difference in the viscosity is also not significantly high, then mu over mu s mostly is very close to 1. Okay, so we many a times neglect that. Okay. All right. Isothermal array of cylinders. So this becomes important. What? Because this array of cylinders is something that we encounter very often. You have already seen examples in heat exchangers, right? In shell and tube heat exchanger, the tubes uh, go in one direction, the flow of the shell make up from the other direction. Okay, so flow over a bank of cylinders or an array of cylinders become very important. Okay, and is very commonly encountered, right? So in such a case, what would be the correlation? Okay, the correlation has a common form. Is C2, as you are seeing here. Okay, C2 times C within brackets C times Reynolds to the power m, Prandtl to the power 0.36, and then Prandtl over Prandtl at the solid surface to the power 1/4. Okay. Are you guys there?
Yes, sir.
Okay. So now the question is, if you look at this term, the C, M, C2, these are all indices. M is an index, C2 and C are constants. So depending on the situation, whether it's an inline array of tubes like this, the left-hand figure, this is inline. Okay. This is so this is staggered. You can see how it is, right? Here they're all in in a certain x and certain y. Here it goes a little crisscross. So the flow will also have to make its way around these cylinders, and the flow patterns will be different between inline and staggered. Okay. Now, what is Reynolds? How is this defined? That's important. Okay. This Prandtl over Prandtl s, you understand, because pretty much comes from mu over mu s. Okay. Because Prandtl is mu Cp by k. But the thing is, this Reynolds, how is that defined? Okay. This Reynolds B max is therefore u or V max. Here it is written as V max. That's okay. The maximum velocity times the diameter over nu. Okay. Now, what is maximum velocity? Because as you can see that as the flow approaches this area of cylinder at a given velocity capital V, as shown here, or U is what we have used in our conventions before. Once it enters the cylinder array, the velocities will be different, right? Because when it is squeezing through, let us say, this area, so of course its velocity has to go up because the area available for flow is low. Again, it will expand. Maybe part of it will go above this, part will come through like. So it's a complicated flow arrangement here. Now, what is the maximum velocity defined? How is it defined? So let me clean up the slide. Use the eraser. Yeah. I don't know why these lines come through. I hope you have written down all these. Okay. So let me write again. Reynolds D max is V max D over nu. V max why? Because when the flow enters here, it is going to squeeze through uh, and it's going to be a little complicated. Okay, there will be some eddies shed probably here. Some of the flow will go like this, etc. So V max is defined in this manner. ST times V over ST minus D times V. What is ST? That's the transverse pitch, center to center distance. That is ST minus dy, because ST minus D, as you can understand, is actually this distance between the two cylinders through which the flow has to squeeze through. Okay, so that is where it comes from. ST minus D, ST times V times ST minus D. So this is V max. Understand? Clear? If you go for staggered array, then it is a little more complicated. ST and SB. SD, as you can see, is defined in this manner. So there are three types of pitches. One is transverse, one is longitudinal, and the other is the center to center distance between two vertical lines of cylinders. Okay, you can say the longer side of the triangle. So if SD minus D is less than ST minus D, then there is something, or otherwise ST minus D, blah blah blah, all that. So this is what it is. Again, these are correlations. You have to just use it blindly. Some people have derived it for us. But all I'm trying to say is you may get relations like this and you have to use them. Okay. So, and again, as another thing I would like to tell here is that even though these are some correlations, there are other people. Correlations have been, multiple types of correlations have been proposed by different people for different ranges of Reynolds number, etc., etc. So you need to keep that in mind. For example, another very famous type of correlation that we come across is called the Zukhauskas correlation for flow over a bank of tubes. So let's not get into all those details. Finally, I would like to make and make a statement here that every correlation is associated with some errors and no single one is sacrosanct. Okay? These correlations, as I said before also, is largely based on a lot of experimental data, and experiments, as always, comes with uncertainties. I mean, if you do some experiment in a setup and I come the next day and do the same experiment, I'm not going to get identical results. There will be, if they're too different, then of course there's a problem. But if they're different, if the results are different within a certain acceptable range or band, then we accept that. And we say that's the uncertainties associated with the measurement. All right. So this is about correlations and this is about external flows. Okay. Now I think I can, how do I escape this? Okay. All right, so that's about flow across sphere, flow across cylinder, etc., etc. I'll just give you a problem for you to solve at home again. Please solve them. Okay, I'm not giving these problems because I have to. Okay, convection, as I said, is largely correlation based. Therefore, unless you solve problems, you will never get hold on the theory, because at least at this level, at the undergrad level, we are not delving too deep into the theory. Okay. All right. So let me give you this problem. Just draw it pictorially here. Let us say this is a cylinder of dimension d. Okay. This is air at 20 degrees C and 1.2 meters per second. Okay. I'm further given that d is equal to 75 millimeter and T wall is 100 degrees C. The air is at 20 degrees C. I'm asking you to find what is Q by L. L is the length of the cylinder. Okay. One thing I can give you that the mean film temperature is 100 plus 20 by 2 or 60 degrees C. And at this temperature, nu is 1.9 into 10 to the power minus 5 meters squared per second. Kf is equal to 0.03 watts per meter Kelvin. Prandtl number is 0.7. No, I don't think you need anything else. You have U with U infinity of d by nu. You can calculate it. And also in part B, calculate the drag force Fd by L per unit length. Okay. Please solve this. The second part especially needs some knowledge from your earlier fluid mechanics. All right, 10:30 now. Let's move on to internal flows. And I'll just start with a small introduction from fluid mechanics again, but then I won't delve too much there and move on to heat transfer. So internal flow just consider flow through a pipe. Okay. You have m dot. Let us say this length is L. The length of the pipe is L. The diameter of the pipe is d. Then there is rho, there is mu, all that stuff. Okay. And at the wall, you are going to have shear stress or shear force, tau w. Clear? So now this is what you are considering. So this, my friends, is internal flow, which is flow through a duct. or a pipe or a tube of cross section AC. Okay. So now if you look at some of the parameters in flow, what do we solve for? We solve for velocity and we solve for pressure. So let us say this is my inlet pressure Pi, and over here I have my exit pressure PE. So definitely PE will be less than Pi. Why? Due to viscous drag forces, this shear force in the wall, right? And so we write that the pressure drop delta P across is Pi minus PE. This is delta P across the tube of length L. And this we know is going to be a function of several things. One is geometry. Is it circular tube? Is it square tube? Is it an annulus? It depends on that. Square, rectangle, whatever. Fluid properties like mu, rho. Okay. Definitely velocity and the length L. Obviously. What is tau W? It's the shear stress at the wall for the surface. Internal surface, because that's where the flow is happening. Okay. So now delta P and tau W are related by the friction factor F. Okay, where F is actually tau W divided by rho V squared by 2. Right? It's a dimensionless number. It is also comes as uh, four dp dz times the cross sectional area divided by C rho V squared by 2. Okay, where dp dz is what? I'm calling this direction as Z. Instead of X, I'm calling it as Z. All right. So a few things to notice. F is non-dimensional. F can be found from Moody chart. Okay. For laminar fully developed flow, F is 64 over Reynolds number. And for turbulent, F is a function of Reynolds number and what is called the surface roughness parameter, epsilon by d. Okay. So this is what one of my friends was asking last time. Remember, unlike flow over a flat plate or any external flow, that is primarily flow over a flat plate, flow in a tube is either laminar or turbulent throughout. And the critical Reynolds number, if Reynolds number less than 2000, it's laminar. And if it's greater than 2000, it's turbulent. Please keep this in mind. This is something I see many people don't have this concept correctly. This 2000 is only for internal flows through a pipe. And there's a reason for that. I'll come to that. Okay. What happens if cross section is not circular? Okay. Then we use a concept called hydraulic diameter, which is 4 times the cross-sectional area over the wetted perimeter. Okay. What do I mean by that? Consider this. Circle, square, rectangle. A, B, and this is B. Try the hydraulic diameter definitions, DH. 4 times area. 4. What is area? Pi by 4, D squared. What is the perimeter? Assuming the flow is completely, the entire cross section is filled, the perimeter is pi E. So therefore, hydraulic diameter is D. We know that. For a circle, hydraulic diameter is equal to its diameter. What about square? Cross sectional area is squared, 4 times that. What is the wetted perimeter? 4A. Yeah. What about this? 4 times AB divided by 2 into A plus B. Okay. Or 2AB by A plus B. So here, what happens is B is much greater than A. So it's a very, very high aspect ratio channel. Okay. So in that case, you will see that DH, what you do is, of course, 2 is there. You divide everything by B. So what do you have? 2A divided by 1 plus B by A. sorry, A by B. And A by B therefore tends to 0 because B is much greater than A, right? Or DH is more or less equal to 2A. Okay. Now, physically, what happens inside this pipe? As the flow approaches, it has a velocity of u infinity. When it comes here, okay, when it comes at the inlet, what happens? At the wall, the flow is restricted. And after that, the flow increases from 0 at the wall, which I can draw a symmetry line through the center. This is an axisymmetric problem. So therefore, what happens? There is a hydrodynamic or velocity boundary layer that grows on the surface. Okay? Just like a flat plate, it will keep growing like this. Okay. Similarly, it's also going to keep growing from the other direction, other side. Okay. It keeps growing, and at some point, the thickness of the boundary layer becomes equal to the radius of the tube. So then what happens? These two boundary layers interfere, they merge. They cannot grow independently anymore, right? Unlike a flat surface where it can keep growing and then transition to turbulent, here it cannot, because its growth is now obstructed by the presence of another boundary layer in an adjacent surface. Any questions? I know that this is old stuff. I know you have already studied this, but it's important to brush up these concepts. Now, similar to flow inside the boundary layer, as we saw in a flat surface, the velocity keeps growing, okay, from 0, and then at the edge of the boundary layer, it is equal to u infinity. And then it remains u infinity. And similarly, there's a growth from other side as well, from 0. I've not drawn it very symmetrically, but you understand what I'm trying to do. So the velocity profile looks something like this. Somewhere here again, something similar, okay. Keeps increasing. Then once it reaches the edge of the boundary layer, it still remains like this, okay. But once it has reached here, then what happens is you have paraboloid profile, I would say, like this. Okay. So once the two boundary layers have merged, it cannot grow any further, right? So beyond this point, the flow remains the same. Wherever you plot, it will be the same flow velocity profile, okay, across the cross section. Okay. So here, this side is called the developed or fully developed flow. And this side is known as the developing flow, or this is also known as entrance region. In the entrance region, the flow develops as if, you know, the flow developing on the lower surface doesn't know the presence of the upper surface. Okay, only when the boundary layers merge do they know and quote unquote feel the presence of the upper surface. Okay. So in fully developed flow, what happens? Mathematically, what do we mean? We mean that del U, del Z, del U, del Z equal to 0. The velocity does not change with Z. Whatever is the velocity at any point, dUr, of course, going to be 0. This flow profile is known as the Huygens-Poiseuille, P-O-I-S-U-I-L-L. Okay, Huygens-Poiseuille flow. Okay, after the two people who solved this. Any questions? This is very important because the effect of entrance length is important. As you know, smaller the boundary layer, it has an impact on tau W because del U del X is del U del Y is high. Okay, so the shear forces are higher in the entrance length. Okay, so now I have a few slides here for internal flow, which I'll share with you. It's exactly what I explained now. You can see it over here. Okay, we have another 3-4 minutes. If you look into this, that is my first slide in the internal flow slide set, which I'm going to share with you. It's important, must distinguish with the entrance and the fully developed regions. Fully developed is where the velocity profile remains uniform thereafter. Okay, but in the inviscid flow region, in the developing flow region or the entrance region, what happens is the velocity profiles at the two surfaces and therefore the boundary layers, the velocity boundary layers, the momentum boundary layers, they grow independently, oblivious of the fact that there is another surface. Okay, and there is what you see, this internal core, which we call the inviscid flow region, which does not feel the effect of the viscous forces at the walls. Over there, the flow continues at an uniform velocity. Okay, the boundary layer thicknesses keep increasing, just like in a flat plate. But however, at some point, which is XFD, which I'm talking about, the position of X where the flow becomes fully developed, the boundary layers merge and we get the fully developed flow. Okay, then this flow is called hydrodynamically fully developed. Hydrodynamically fully developed. Why I'm saying hydrodynamically? Because very soon we are also going to talk about what is called a thermally fully developed flow. Okay, we will cover that cover this on Wednesday in more details. But here also, similar to a momentum or hydrodynamic or velocity boundary layer, there will, if you consider flow through a pipe which is heated at its wall, there will be a thermal boundary layer which is going to form. The temperature of the fluid is going to be equal to the wall temperature at the surface and then slowly reduce. And at the edge of the wall, edge of the boundary layer, edge of the thermal boundary layer, it is going to be equal to the fluid, means the entrance temperature, right? But then the thickness of the boundary layer keeps growing. Just like in hydrodynamic region, there will be a thermal entrance region, and then there's fully developed region, where now you are going to get a thermally fully developed temperature profile. Okay. However, the definition of fully developed for thermal is a little different. Here the temperature will still keep increasing and the profile will also change depending on the surface condition. Okay, why? Because there is still flow of heat. If something is absorbing or rejecting heat, the temperature has to change. Okay, so the temperature will change. There is something else that determines what is mathematically defines what is fully developed, and we will come to that. Okay, all right, let me stop here today. And before we disperse, stop sharing. Before we disperse, let us again make sure what we discussed at the end of the last lecture, and that is about your class test 2. Your class test 2 is going to take place on Saturday, 30th. 30th of October. This is as per your wish. It's on 30th of October will be your second class test. I'm going to confirm the time on Wednesday or Thursday. And the reason is as follows, because on Saturday, I myself have an engagement in the morning. Okay, or throughout the day actually, where I have to go out of station. So I have to see what is a convenient time or whether instead of me, the TAs can conduct the test. I'll finalize all those and get back to you with the exact time. Okay, it can either be in the morning or it will be in the afternoon. Okay, all right. And then what I will do is I will also right away, I'm going to announce the date for your next class test. Okay, and that is going to be on 13th of November, which is a Saturday. Okay, please keep that in mind. Don't tell me later that I have another test, I have already committed to that and so on. Okay, so your second class test, the syllabus for which is radiation and heat exchangers, is going to be on 30th of October. The third class test, which is going to be on convection, forced and natural, and maybe boiling and condensation as well, is going to be on 13th of November.
Excuse me, sir.
Yes.
Sir, I think 11th to 14th, there is another slot for students coming back to the campus. So there, actually, it's not confirmed till now, but there is a possibility that from 11th to 14th, students might be called back. So
11th to 14th, what is the last day of your classes?
the 20th.
20th is the last day of class. Okay, in that case, we will do it on 20th. Is that okay? All right, so your third class test will be on 20th of November. That puts a little bit pressure on us because we have to grade and upload the grades by, I think, 1st of December. But okay, fine. So your class test 3 will be on 20th of November. Let me note it down also. All right. Thank you very much, everyone. 10:59, and see you on Wednesday morning. I'll stop the recording now, but as always, I'm going to stay back for some more time to answer your doubts and questions.